This video is on different laws that we will be using within probability. So we have the addition law, the mutually exclusive, independent and conditional. Now some of the notation and symbols are in this box that you start with first for intersection, union, complement and conditional, what the informal language is and its formal definition. But we're just going to go through and talk about each of them separately and what rules actually link with each of those ideas. So the first of all, the addition law for probability is the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Now I have to note and stress that you always use this formula unless you are told events are independent. One of the biggest mistakes that gets made is people use a formula for independent events when they're not independent. So always use this rule unless you are told independence exists. Next, we have mutually exclusive, which is when the intersection of two events equals 0. So you can see I've just got a little Venn diagram there, which shows that the circles do not intersect. That is mutually exclusive, so there is no intersection. Independent, which means that one event does not affect the next event happening, and that's when we have the probability of A times the probability of B. Conditional probability is when we have the probability of A and we draw a straight line, B, and that is equals the probability of A and B over the probability of B. Now, the wording of this is the probability of A given that B has occurred. So you always have your first letter. We're finding the probability of the first letter occurring given the second letter has occurred in that equation. And very often the word given is used in the questions, which is then kind of the big light bulb moment of, oh, given. More than likely conditional probability. The last little law is a complementary probability law. We all know complementary events mean that it's the probability of it not happening. So the complementary event of the probability of A happening is A not happening. So there's just a little laws here which are pretty self-explanatory. So the probability of A equals 1 minus the probability of it not being A. And that the probability of A and the probability of not being A will add up to 1. So a few examples to kind of cover all of the different laws. If the probability of A equals 0.6, the probability of A or B equals 0.7, and the probability of A and B equals 0.3, find B. Now in this, we are not told about any independence whatsoever, so we need to use the addition law, which I will just write out here, which is the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Put in everything that we know. So we know that this is 0.7 equals 0.6 plus the probability of B, which is what we're finding, minus the probability of A and B, which is 0.3. So I'll end up with 0.7 equals 0.3 plus the probability of B. The probability of B will equal 0.4. Next example, a class of 30 students was given a history test. 7 students scored an A, 11 students scored a B. A student is randomly selected. Let A be the event the student scored an A and B be the event the student scored a B. Are A and B mutually exclusive? So mutually exclusive, remember, means we cannot have both events happening at the same time. So have a think about it. Can a student get an A and a B on the same test? And the answer is no. You either get an A or a B. It's not possible to get an A and a B. So yes, they are mutually exclusive. Okay, part B. Just finding some different probabilities. The probability of A. So the probability of that a student scored an A. We look at the information we've been given. 7 students scored an A, which means it'll be 7 out of the total class, which is 30. Part 2, the probability of event B, which is that they scored a B. We look there, that was 11, so that would just be 11 out of the 30. 3, probability of A and B. So what is the probability that a student got an A and a B? We already know that's not possible, which means it would be 0. And the last one, we want the probability of an A or B. Now with A or B, we know they're mutually exclusive, so there is no intersection. So you could use the addition law from before, if I just scroll back up, this one here, but we know the A and B section is going to be 0. So we're going to be having probability of A plus probability of B minus 0. So we can here then just do the probability of A, which is 7 over 30, plus the probability of B, which is 11 over 30. And we can just do the minus 0, so we're remembering we're still using that rule, and this will give us an answer of 18 out of 30, simplified down to 3 out of 5. Example 3. A coin is tossed and a die is rolled simultaneously. Determine the probability of getting a head and a 3. Now sometimes in this situation we've got to think logically about this. With this question we are trying to find then the probability of it being a head and a 3. Now this question does not tell us that it's independent, but then sometimes we do just have to use our brain and go, if we're tossing a coin and rolling a die at the same time, do they affect one another? Are those two things completely independent of each other? Yes, they are. Rolling the die does not affect tossing the coin, which means it is going to be an independent event, which is the probability of the head multiplied by the probability of a 3. Probability of getting a head is a half. Probability of rolling a 3 is 1 out of 6, which means we get 1 out of 12 for our total probability. Example 4. Carl is not having much luck lately, poor Carl. His car will only start 80% of the time and his motorbike will only start 60% of the time, independently of one another. Draw a tree diagram to illustrate this information. So first of all, we've got a car and a motorbike, so they will be our two little strands. So we're going to start with first a car. The car starts 80% of the time, which as a probability is 0.8. So we'll go start and N, so start and not start, which means the probability of not starting is 0.2. Then we're going to look at the motorbike, and that starting and not starting. So motorbike starts 60% of the time, so 0.6, and so 0.4 for not start. We want to use a tree diagram to determine the chance that on the next attempt, both will start. Carl can only use his car. All right, there are two things. So if we look at our outcomes, we have the outcome of them both starting, the car starting, the motorbike not starting, car not starting, motorbike starting, and then them both not starting. Now remember, we multiply across to get the probabilities. For the first one, we would have 0.8 times 0.6, which is 0.48, and we do that for each one. Sometimes it's just a good idea to work out all your probabilities like this in the tree diagram, because then once it comes to actually working out which probabilities you need, you've already got all your information there ready to go. So we want the probability that the car will start and the motorbike will start, which is SS, so it's just the first one, which is 0.48. And then for part 2, we want Carl can only use his car, which means we don't want to be using the motorbike at all. And so that will be this one here. So we want the probability of the car and not the motorbike, which will be 0.32. Last example in this section. In a town, 25% of the residents own a cat, 55% own a dog, 30% do not own either. Draw the Venn diagram. So there's a bit more Venn diagram practice here. So start with your rectangle. We've got cat and dog as our options. So that will be our two circles. Start with the information. So we've got 25 on a cat, 55% on a dog, and 30% do not own either. So the one we can definitely put in first is the 30%, so the 0.3 on the outside of the circles. Now we have to work out now where things go in the middle. And to do this, we can use our addition law. So the probability of C or D equals the probability of C plus the probability of D minus the probability of C and D. Now, C or D, we do actually know this because we know that we have the 30% on the outside, the 0.3, which means the circles must add up to 70%, so 0.7, because we know the whole thing has to add to 100%. Probability of C, so a cat, we're told in the question is 25%, which will be 0.25. Probability of dog, we're told is 0.55 or 55%. So this means we can find out what the intersection is. When we solve this, you'll find that the intersection of cat and dog is 0.1 or 10%. So that can go in the centre of our diagram. Now we have that, we can work out the rest. So we know cats is 25%. We've already got 10% or 0.1 there, which means we have 0.15 left over or 15%. Dog, we have 55% on a dog. We already have 0.1 in the circle, which means there is 45% left over or 0.45. And that's our Venn diagram. Part B, find the probability that a randomly selected resident owns a cat given that they own a dog. So we want the probability that they have a cat given, which is a straight line, they own a dog. So we want to use our formula, which is the probability of C and D divided by the probability of D. And we just put in our information. Probability of C and D is 0.1. Divided by the probability of D, which was 55%, so 0.55, the probability of having a dog. So this simplifies down to 2 out of 11. Then part 2, we've got does not own a dog given they own a cat. So the probability of the complement of a dog, so does not own a dog, given they own a cat, so the line C. So this will be the probability of not D and C all over the probability of C. Not D and C, look at our Venn diagram. Not D and C will just be this 0.15 part here. So 0.15 divided by the probability of a cat, which from the question was 25%, so 0.25. Simplify that and you get 3 out of 5. And that is all the probability laws that we will be doing.